Right, so let's move on to the tutorial regarding one-way slabs. The question back on page 34 was a one-way slab, similar to the worked example in the lecture notes, but the live load had been increased to 5 kilonewtons per square meter. And this is the arithmetic regarding that. It's all, the only thing that's changed in the given is the live load's gone up 2 kilonewtons per square meter from 3 kilonewtons per square meter to 5 kilonewtons per square meter. So I've said, note, as the assumed, in doing the solution, as the assumed slab thickness on page 32 was more than adequate, we will, despite the increased live load, despite that increase to there, use a slab thickness of 200 millimeters. So our slab weight or slab mass, 0.2 times 24, 4.8 kilonewtons per square meter. Sorry guys, per square meter. It enables me to correct my tutorials before I post them up to you. And then your factored loads are 1.2 times the dead load plus the finishes plus the live load. 1.5 times 5 kilonewtons per square meter gives you a total load of 14.46 kilonewtons per square meter. Now the moment is WL squared over 8 again, which gives you a bending moment of 45.19 kilonewton meters. And here I've assumed a bigger diameter of bar because as the moment's going to be bigger due to that extra live load. Using 20 millimeter cover and 200 thickness in this particular case, our effective depth is 172 millimeters. 200 minus the cover minus the radius of the bar, 172 millimeters. From the chart, we can work out, assume a P, which is based on the area of steel over BD, 0.012. Then M over BD squared, which is lambda, gives you 4.3. And going down then, working out what effective depth you require with a lambda of 4.3, we find that 102 millimeters theoretical would be sufficient, which is less than 172. But when you come to start doing deflections, as we will do in the next lecture, you'll find that it's not a straightforward case of saying, well, that's adequate. You have to take deflection into account. So at this stage of the lectures, we're just assuming a heavier section to cater for deflections. Now, moving on, the actual moment divided by BD squared, which is your lambda, along the bottom axis of the graph, is 1.52. The moment, converted to Newton millimeters, unit width of slab, which is 1,000 millimeters, 1 meter, by the effective depth squared, gives you a lambda of 1.52. And from your chart then, the steel ratio is 0.004, which is greater than the minimum that you're allowed to use as per clause 9.1.1b. So that's okay. Area of steel you need is PBD, and that works out at 688 square millimeters per meter width. Because you are working in meter widths, keep emphasizing that. If you look up in your charts and you choose steel, let's have a look at that one. Let me find the right chart here. I've included 2 charts for you for selecting reinforcing steel. You can use either one, it depends on what spacings you want to use. Oh, goodness me. I've located the sheet eventually, and I'll certainly include this in your lecture notes that get posted on Connect. But if you look at 16 millimeter bars at 275 centers, gives you 727 square millimeters, and you need 688 square millimeters, so you're fine. You can use N16s at 275, which is 727 square millimeters. Now, the shear capacity you have to check. The total shear on the slab is the load per meter multiplied by 4.7, the clear span, Ln, between the supports. Gives you a figure 33.98 kilonewtons. Designers often don't sort of go to those depths, or those lengths, should I say. They will just take the full span divided by 2, which I've done in a later problem here. Shear capacity with no shear steel, tension steel only. You're familiar with this from your shear lecture notes. Area of steel over BVDO, which equates to PV, which you can then look up in your graph. And PV is 0.004. Using your shear charts, then you can work out what the shear strength of this beam is based on that area of tension steel. And it is 60 kilonewtons. As I said earlier, shear is very rarely a problem in slabs. So you've got a shear resistance of 60 kilonewtons. The actual shear force is 33.98 kilonewtons from that. No problem, so it's okay. Temperature steel or distribution steel, whichever way you wish to call it, 0.002 of the cross-sectional area of the slab, 0.002 times the width of the slab, 1,000, thickness of the slab, 400 square millimeters. Again, we'll use N12s at 275, okay, which will cater for 400 square millimeters. Moving on then. So that slab is done. And getting on to question 2 now, which is on in your lecture notes. Question 2 was a 3-span beam with a live load of 3 kilopascals, ceiling floor finish 1 kilopascal, concrete strength 32 MPa, normal yield strength in high tensile steel 500 MPa, and A1 exposure. For the solution, we're going to use those moment and shear factors from AS 3600, 7.2, to calculate the moments and shears. And I showed you those earlier in a little sketch I made while I was delivering the lecture. And when you look at those, you'll be able to identify them. Yeah? Your moments, which are written up in pencil, your shears are written up in red. But your moment at the center, approximate center of the span, is WL squared over 11 from those tables. Your moment at the support, the negative moment there, WL squared over 10. In an internal span, positive moment, WL squared over 16. And because of symmetry, that's exactly the same as that, and that's exactly the same as that. These are your shear forces computed on the basis of the tables given to you. This is the only one that's elevated or escalated, the shear force to this side of the support, which is 1.15 multiplied by WL over 2. So just to show you the moment diagram now, I'll jump ahead. This is what that moment diagram will look like. We'll go over this again, but that's what it's going to give you, the moment diagram. And these are the shear forces as given to you in the tables. Right, so going back here, we've got the beam with a 4.5 MPa live load and a 6.1 dead load, 6.1 meter dead load. Assume a slab depth, in this case, of span over 35, 171 millimeters, as the moments are low due to continuity. As soon as you have continuity over many supports, the bending moments get smaller. So you can start to have thinner sections. You get more bang for your buck, in other words. So looking at the loading on the slab, the slab thickness is 0.17 times 24 kilonewtons per cubic meter, which gives you 4.08 kilonewtons per square meter. That's the weight of the slab. The effective depth that we're going to use to work out our steel and so forth is the overall thickness of the slab minus the cover minus 6 millimeters, assuming we're going to be using 12 millimeter diameter bars, which gives you an effective depth of 144 mil, as you'll see later on. These are our factored loads for dead load, 4.08 self-weight of the slab, plus the 1 kilonewton per square meter finishes, plus the live load, 1.5 times 3. Total of 10.6 kilonewtons per square meter. Now, these tables take cognizance of the fact that your moment envelope will change, and that's why they've been adjusted. Those factors have been adjusted to allow for some spans being loaded, other spans being unloaded. I've been over this with you previously, drawing moment envelopes, and if you're using Space Gas program, it does it for you automatically. In this case, these factors allow for that. So looking at the points where we want to take moments today, there, moment in the beam there, this negative moment over the support, that moment there, these are all going to be the same because it's a 3-span beam that's symmetrical around the center. So looking at MB, which is in the middle of the first span, WL squared over 11. W per square meter times the span squared over 11. The moment is 34.7 kilonewton meters. The moment at C, there, the negative moment, 38.16 kilonewton meters, just WL squared over 10. Just to reiterate, it's the load on that span times that span squared. And you'll see that I haven't haven't assumed a width for these supports. I've worked center to center to center. If you know what they are, then you could actually work it differently, but you're on the safe side doing this. That's the moment at C. The moment at D, which is the positive moment in the center of the whole 3-span beam, the moment at D is only 23.85 kilonewton meters because the factor is very small, WL squared over 16. Your shear forces, the one at the external support is just the load over half of the load, 10.6 times 6 meters, a half of that, 31.8 kilonewtons. Your shear at your first internal support on this side of it is 1.15 multiplied by that. That's given to you in the set of tables. The ones that you're looking at, VE and so forth, and on this side of C are purely load divided by 2, gives you the shear force. And to come back to the diagram then, if you sketch this out, and it might not look as nice and tidy as this if you took into account the fact that there's a moment envelope, but I've sort of encapsulated all this in a 3-span beam moment diagram. With your positive moments, I've assumed that there's no fixity there, there's no connection between the slab and a beam. It's simply supported on a brick wall, I've assumed. So there's no bending moment there. Your maximum moment from the computations we've been doing is 34.7 kilonewton meters there. Your maximum negative moment at the first interior support, where the beam, the beam follows, in deflection follows the bending moment diagram like that. That's why we draw it upside down. Makes mathematicians' hair stand on end because we were putting a positive below the baseline, but it suits structural engineers, okay, around the world. There your maximum negative moments are. By symmetry, same on this side. So that's your bending moment diagram. These are the shears given to you in those tables. It's at 1/7 at the center. That's of pure academic interest because your beam will handle that quite easily. It's a load over 2 for the end. But at this first interior support, just to the left of the support, it is 1.15 times that load. So there you have a set of shears. And the shear force is computed on the basis of the load per square meter multiplied by 6, and then divided by 2, or divided by 2 times 1.15. And all this is the simplified method as per 721. Now, calculating the area of steel for the different moments, we just look for the lambdas in each particular case. I'm not going to grind through this because I've done this many times with you in this course of lectures, and by now you guys should know what lambda is. You know it's m over bd squared. B in the slab is 1,000 millimeters, and it gives you a factor lambda 1.67. Using that, you can have a look at what your steel area is, and hence computing your steel area, looking at your tables for a 590 square millimeters, you can use N12s at 175 centers. Then you look at the area of steel for the moment at C and repeat the process and see what steel area you need there. For MD, moment at D, getting back to the diagram there, the moment at D is this positive moment there. It's only 23.85. But the moment at D gives you a lambda of 1.15, and you can use lightweight steel, the N12s at 250. You can check the shear capacity of your slab. The total load 36.57 VC. So the shear capacity using tension steel only. Your area of steel at C is 691 divided by BVDO. And again, we've done this in the shear calcs. I mean, if you look back earlier in your lecture today, you'll find this computation. But if you look back at the shear that we did in beams, it's essentially the same, except that the breadth for a slab we take as unity, 1 meter. And we find, having done all that, using your shear charts, we find that the strength of the beam is 54.72 kilonewtons, much greater than the actual shear force on the beam, so it is okay. Your temperature steel, according to code, 0.002 of the cross-sectional area, a 1 meter wide strip by the thickness of the slab. 170,000 times 0.002 gives you 340 square millimeters. And if you use N12s at 300, you can check these up on the steel chart. It gives you an area of 367, so that is adequate. And I've said NB, the slab should be checked for deflection. We haven't done deflections yet, but you will be doing them shortly in the next few lectures, and then you'd be able to come back and check this slab for deflection. I've made right, I've drawn a cross-section through the slab there, this one-way slab that spans between the grid line A to B to C to D, 6 meter spans. We don't know what size beams those are. We've decided on a 170 thick slab, and this is the first 2 spans, actually, A to B to C, A to B to C, but at an enlarged scale. And it's not an exact scale, but it gives you some idea of slab detailing. And this will be the sort of thing that will probably turn up in your assignment. So I've drawn the steel right through. I have not curtailed the steel as the code says. I've just run those bars right through. You have N12s at 175, which are your main bars running that way. Was it 175? Let me check on that. Something just tells me it was N16s, but let me just have a look. It could have been... N12 at 170. N12. No, that's I was wrong there. It is N12s at 175. That's your main bars. N12's at 250 there because your moment was much smaller. Do you remember in this center span, your moment was a lot smaller, so you end up with N12's at 250s. This is where the bars just run over past each other. They're lapped against each other over the beam. These dots that you see there is the temperature steel, the transverse steel. It doesn't run through the beam because remember that you've got beam steel in there, a ligature, and you've got your main beam steel. So you can't, it's pointless running these bars through the inside of that. They don't serve any purpose. Or at the top, because you've got tie bars for your beam over there. And in fact, this negative steel there rests on top of the beam steel. So that's an important factor, but I'm sure that you've done this in Revit. So you should know about detailing that, but I will just show you what I'm talking about. If you've got, let me find a new page. I don't want to waste too much paper, but if you've got this situation like this, you've got your beam there, you've got your beam steel that will go in there, which I haven't shown, of course. You've got your beams, those are your ligatures, two tie bars there, maybe lightweight tie bars, N12s, whatever you've got here, N28s or whatever. Then you've got your main slab steel coming through to there, and the other one for this span runs through there. You've got your negative steel, the negative moment resting on top of that. That's how it's fixed. It's tied onto those ligatures. This beam steel is the sort of spine of the thing, the basis. And then you've got all your temperature steel tied below that or on top of this for reasons that it's not tied to the outside because you want the maximum effective depth you can get for structural purposes. That's why all this temperature steel is on the inside of the steel, because you're looking at the maximum, you know that your effective depth is from the center of the steel there to there, or from the top of the slab to the center of the steel. And if you put this, if you tied this temperature steel below it, you wouldn't have as big a effective depth. That's important. This negative steel I've poked out into the span 0.3 times the 5,600, where I've sort of made some assumptions on a beam width of 400. That's LN, of course. That's 0.3 times 5,600, 1.7 meters. And that way you can compute how long you should make your negative steel. As I said to you, I've ignored any negative steel on this edge. I've just assumed that the structure is simply supported on that end. So all these little dots are N12s at 275, and they run from there to there, transverse, right angles to the paper, right along the beam, slab, sorry, right along the slab. All those dots, I haven't shown all of them, but they're all there. They're all at N12s at 275, as are the top there, N12s at 275. Stops cracking, shrinkage, and so forth. So there's a part section for you to contemplate, and that winds today up. Thank you.